Welcome to example number 9. We have an infinitely long rod with a uniform charge density of lambda. We're asked to calculate the electric field at a distance of r away from the wire. So the first step in applying Gauss's law is to identify the symmetry that is associated with the charge distribution. So what we're going to do is we're going to look at this cylinder and look just at the cross section and draw that so that we can look at what the electric field looks like for a cross section of this conductor, which is basically in the shape of a cylinder. So here you have a picture, and hopefully you will see that the electric field points radially outwards from the axis of this cylinder. So what we need to do is find an appropriate Gaussian surface on which the magnitude of the electric field is constant over portions of that surface. So we choose a coaxial cylinder as our Gaussian surface. We chose that because along that surface you'll see that the electric field at all the points along the surface will be constant and also will be radially outwards, which is perpendicular to that cylinder that we've chosen. In a minute, we're going to look at this Gaussian surface, but let's go pay attention to question B, which is asking for the electric field that is inside this cylinder. And I hope that you will realize that the electric field that is inside that cylinder will be 0. The reason we know the electric field is 0 is because we have a conducting cylinder, which means that the charge will all move to the outside of this cylinder. Now let's move on to part C, which is to find the electric field at a point P away from this long conducting cylinder. So what we're going to do is draw now just a picture like this from the side view of this Gaussian surface in the cylinder that it was a long conducting cylinder here. And so here's another picture of the Gaussian surface in blue and this uniformly charged rod with a uniform charge density lambda. So we're now going to divide this Gaussian surface into 3 parts. The 2 end caps, this end, and then the cylindrical surface around the wire. So we're going to look for the flux through 3 different regions. Surface 1, which is this left end cap, surface 2, which is the right end cap, and then surface 3, which is this cylindrical sidewall. Okay, so now to find the total flux for this Gaussian surface, we're looking at the closed surface S, which is really this whole Gaussian surface, and we're taking the integral of that closed surface E dot dA. We're going to break this up into the 3 different parts. We have the integral along surface 1, E1 dot dA1. We have the integral of surface 2, E2 dA2, and then we have the integral along surface 3, that's E3 dot dA3. If you look along surface 1 and surface 2, the 2 end caps, you can see that the angle between the electric field and the area vector for that little piece of shaded area, it's 90 degrees, and so as it is over here. So none of these field lines actually penetrate through the surface. So hence, the flux through surface 1 is 0, and the flux through surface 2 is 0, and really all we need to concentrate is the flux through this cylindrical wall. So the total net flux is really equal to the electric field, which is constant along this cylindrical wall, multiplied by the integral of dA3. So really this is the area of this cylindrical wall. So you can imagine that you're going to unravel this cylindrical wall, and think of it as, well, let's call this length L. That's the length of our Gaussian surface. So this is L. And then if you unravel around this, hopefully you will think of this as the circumference, which is 2 pi r. So the area of this cylindrical wall is E times, this is our flux, E times 2 pi r times the length of our cylindrical cylinder. Now, if you recall, Gauss's law says that the total flux is equal to the Q enclosed divided by epsilon naught, which is now equal to E times 2 pi r L. Now, the Q enclosed by this Gaussian surface here, if you recall earlier at the top of the page, we talked about the linear charge density being equal to that little piece of charge dq over that little length dl. So therefore, if you're doing it for the whole entire surface, you could replace lambda as being equal to really the q that is enclosed divided by the total length of our Gaussian surface. So therefore, our q enclosed is really the surface charge density lambda multiplied by L. And this is all divided by epsilon naught. And you'll see the length of our cylindrical Gaussian surface, L, will cancel out. Now remember that this r here represents the radius of our Gaussian surface. So that's that point r where we're trying to find the electric field. Rearranging for our electric field, we find that E equals lambda all over 2 pi epsilon naught times r. And this is for r greater than the radius of this wire. Remember that the electric field inside here is going to be 0 when it's less than the radius of this wire. Okay, the next thing we want to do is we want to sketch the electric field versus the distance r from the center of the cylinder in the graph shown down below. So we have two important things to realize. The electric field inside is going to be 0, and the electric field will be equal to this expression when r is greater than the radius of our long conducting wire. So that means the electric field will be 0 all the way until it reaches r, and then it will reach its maximum peak, where the magnitude of E at this point will be equal to lambda divided by 2 pi epsilon naught, and r in this case will be equal to capital R. And then as r approaches infinity, you'll see that E will decrease. This is an inverse curve, so it'll start to look like this. So you'll see that E is inversely proportional to R. Okay, now for a little bit more challenge. What would happen if this cylinder was non-conducting? So that means in the first part, you notice that the electric field was 0 inside the metal cylinder because it was a conducting cylinder, and hence all the charge resided on the outside surface, which meant the electric field inside would be 0. But what would happen if this cylinder was non-conducting? It was insulating. So how would we solve this problem? I'm going to need a little bit more paper, so you may want to pull it next to your sheet, and we're going to solve this on a separate page because obviously I don't have enough space for part F. So we're looking for the place where r is less than the radius of the cylinder. Let me draw a picture for this. And there you have it. There's the wire shaded in orange, and then I've selected a Gaussian cylindrical surface within the wire with radius r and length L. If you were to look at the cross section of this cylindrical wire, you'll see the following. And with the electric field lines all pointing radially outwards from the center point here, and hence the electric field would be constant at all those locations along the Gaussian surface. However, since this is an insulating material, non-conducting, then the charge will be linearly or uniformly distributed throughout here. So there'll be charges all over here. Then we would divide the Gaussian surface into 3 different regions: the left end, the right end, and then the cylindrical wall for their Gaussian surface. And now we'll find the total flux of this Gaussian surface, which is the integral over this closed surface E dot dA, which is really made up of 3 surfaces, S1, S2, and S3. But, as it was in the last problem, S1 will be 0 and S2 will be 0 because the area vector is perpendicular to the electric field. So the two ends will have no flux, and really we only have the flux along the cylindrical wall. So the total flux will be equal to E multiplied by the area of the cylindrical wall, and if you recall, that was 2 pi r times L. And this is equivalent by Gauss's law to the charge that is enclosed, Q in, divided by epsilon naught. So the electric field will be equal to the Q that is enclosed divided by the area, which is 2 pi r times L times epsilon naught. So we now have to find out is what is this Q that is inside relative to the total charge Q. And we know that the charge distribution is cylindrically symmetric for this charge density. That means the volume charge density rho, which is equal to the charge inside that Gaussian surface divided by the volume, or the charge inside that surface divided by the volume, which is the volume of a cylinder. This Gaussian cylinder with a radius r and a length L would be pi r squared times L. Therefore, we could replace Q inside this Gaussian surface with rho times pi r squared L in this expression. But we can also get rid of this density and write that density in terms of the charge density for the entire cylindrical wire. So that would be the total charge Q divided by the total volume. Now in this particular case, we know that the wire is infinitely long. But for now, I'm just going to call this distance d, even though d is really infinity. So that volume charge density will be equal to Q divided by the volume of this cylindrical wire, which has a distant length d and has a radius r. So we'll be writing pi capital R squared times d. But we would probably prefer to get rid of this total charge Q and put it in terms of lambda 2, this linear charge density. Remember, that is equal to the total charge divided by the length. And in this case, our length of the wire would be as infinity, but we're going to just put it as a d. Therefore, the total charge Q of our wire would be the linear charge density multiplied by the length of the wire d. So let's substitute that into here. We get lambda 2 times d all over pi r squared times d. And the length of our infinitely long wire cancels out. So let's now substitute this expression in for here. And there we have that. And then you should be able to cancel a bunch of things from top and bottom. And you'll get this final expression here for r less than the radius of the cylinder. So then one might ask also, what would the graph look like if you were to graph the electric field as a function of r? So if you look at the region from 0 to r, you can see that when we plug in 0 for little r, the electric field will be 0. And then when we plug in r equals capital R, you get the same expression that we got before, which we did in the earlier page right here. Except we are now just changing lambda to lambda 2 for the second type of problem. So therefore, what would that look like between here and here? And hopefully you guessed it. It's a linear relationship. You've already seen something like that. And as we had before in the past, for r greater than bigger R, nothing's really changed now. It's the same as the earlier problem, which was this expression. And if lambda 1 equals lambda 2, then it will join right up here, and you'll get this nice inverse curve here, where E is inversely proportional to R. And hopefully you'll notice this is very similar to the non-conducting solid sphere we did earlier in example 8, as shown down here, where you look at the graph and we had something like this, except now it was 1 over r squared for a solid sphere that was non-conducting. And I should mention as one final word with example number 9, we've been assuming that this cylindrical wire is very, very long, essentially infinity. If it weren't very, very long, it was a finite length, then we wouldn't be able to do this. Because all along for our Gaussian surface, we've been assuming that this electric field is perpendicularly out. Now, if it was, it's only true as long as this end and this end extend out to infinity. If you didn't have an infinite length here and this was a finite length here and here, then what would happen is then you would have not just a perpendicular component of the electric field, but you would also have parallel components. Thus, the condition where the electric field was parallel to the area vector and we were able to solve that integral very easily, then we wouldn't be able to do that if this was a finite length. All right, and that's it for example number 9.